I will more concentrate on the single line diagram part and the how to decide various protection and other services required for given power plant. So, I have just one slide here, hope that it is clear to you, but it does not matter if you can't read it. You can see there are, this is a actual power plant single line diagram. This is a power plant in that has been implemented and in operation, right. So, there are two machines, machine number 1 and machine number 2, and we can see the generator here, right, generator synchronous brushless generator 1, generator 2, and then synchronous breakers, and then the generator transformers and so on. And now it has various protection schemes, measurements, and you can see here in the neutral earthing, and then there is CT measurements and also a neutral earthing resistor, and all these things are who governs that, who decides that, how an engineer can decide what protection schemes and what way the scheme should be implemented, right. That is the subject that we are going to discuss today. For that, each electricity authority has published what is called a grid code, right, grid code. So, the grid codes are available in every utility depending upon its own technical parameters, and protection requirement. So, this is the grid code applicable in Sri Lanka, right, published by Ceylon Electricity Board. So, if we are going to construct a power plant, this is applicable not only for hydropower plants, it is for solar, wind, for any technology this is applicable. So, this is for, that is why they call it application evaluation and interconnection procedure, December 2020 to guide for grid interconnection of embedded generators, right, guide for grid interconnection of embedded generators, right. So, it is applicable for any type of embedded generator, that is generators coming into the distribution network, right, generators coming into the distribution network. So, we will go through this, but whenever you are doing a project in any area, any utility, you must get hold of the corresponding grid code, and also there are grid codes for different purposes. There are transmission grid code, right, transmission grid code is for transmission network design. So, it is not applicable for this. So, for small hydropower, solar PV and other things which are going to be connected to distribution network, for example, 11 kV or 33 kV networks, we must use a embedded generator interconnection guideline, right, interconnection guideline. So, this is in two parts, we can't go through the entire book. So, we will just go through some important areas and see, get a bit familiar, then you can use your own utilities grid code, right. So, you can see, so it is defining what is embedded generator and so on, and then various operating conditions like say islanded operation, grid system security, availability of capacity, grid capacity, embedded generation and system load, system reliability and stability. So, all these things are subject matters of this guideline, and how you can make an application, and how CB will check, or the utility will check the grid connectivity, right, and then it gives the format for form of initial application, form of letter of intent, forms of information to be exchanged and so on. So, all of these things are there. So, once if your project is grid connectable, utility will issue you a letter of intention, that is they are willing to take up your project and grid connect. They have allocated the grid capacity for you, right. So, they will allocate that, right. So, let us go further. So, there are general definitions and abbreviations and so on, various preliminary information are there, we will skip them. You can see it says embedded generators have been connected to Ceylon Electricity Board system under power purchase agreement since 1997 and so on and so forth, it gives the background. Then it gives the definition of all the terms applicable to this. For example, this is a good place where you can know things exactly, right, without having ambiguity. For example, what is neutral point displacement voltage, what is NVD, right, and all these things you can know without doubts. So, that is why the definition part is very important. Some are very familiar to us, some are not. Or voltage or frequency, these are familiar to us. Then point of common coupling, point of supply, they are legal definitions. Otherwise, when you go to courts over some matter, there will be ambiguity, right. Then Rocoff, that is rate of change of frequency protection, reverse power, standby earth fault, spinning reserve, step voltage, all the definitions are here. Touch voltage, transferred voltage, TNS system, TT system. In Sri Lanka, the earthing system is TT system for the low voltage installations. Vector shift protection. Then the scope of the guide, right. So, the guide for interconnection of embedded generators in Ceylon electricity board system in Sri Lanka is a comprehensive analysis of issues and provides guidelines in determining the processing of inquiries, types of interconnections, voltages, studies required, protection requirements, and the testing and certification procedure of embedded generators. General information is also provided on interconnection protection system and earthing. So, all these things are included in this guide. I will not read everything, I will just browse through it with you, and important points I will here. It defines what is an embedded generator. Embedded generators are typically small and medium sized generators which are connected to the distribution system. There may be also be captive loads. The interconnection voltage would be 400 volts or 11 kV or 33 kV in Sri Lankan context. So, the types of plants are embedded generator is being encouraged to utilize energy sources available across the country. These resources consist mainly of hydropower schemes, but also will include combined heat and power, wind power, and possibly also other sources of generation. Then it defines the islanded operation. For the purpose of this guide, islanded operation is the situation that arises when a part of the electrical system is disconnected from the main grid and is energized by the embedded generation connected to it. So, this is there is a safety requirement, right, safety requirement. Suppose we are having a generator running in connected to the distribution network, and somewhere maybe upper side of the distribution network feeder some breaker trips, and this generator and part of the distribution system is working in in synchronism. So, that could be dangerous, because then unknowingly the service personnel might come and try to correct the whatever the fault that occurred while the system is energized, part of the system is energized. Therefore, it is required that if a breaker trips by any chance grid system breaker trip, the plant should shut down. Grid system security. I will again skip some of these sections, but if you are really doing a project, you must go through the guide when designing the system. Here is a typical distribution system with embedded generators. Just make it a little smaller. Here you can see a typical system they are giving, right. Okay, I will enlarge it and we will look at it part by part. This is the grid substation. we looked at it some concepts earlier also, right. So, 130 kV grid substation, where you have this usually the capacity of these transformers are 31.5 MVA, and you can see then afterwards you have the 33 kV feeders, and then we connect the embedded generators at different levels. You can see customer loads are there, delta star distribution transformers are there, right, and here is a HV connected generator, right, HV connected embedded generator. So, it has a step up transformer, and the point of supply is here, right, point of supply is in the HV side. So, therefore, the metering will be on the HV side, right, metering will be on the HV side, right. So, interconnection protection will be there, but here is a LV connected generator. You can if the plant is not very large, they might allow you to connect it to low voltage system, say a 500 kilowatt plant, they might allow you to connect it to a low voltage side. So, it is connected here, you can see 400 volt side, 400 volt side, and point of supply is here. So, the transformer belongs to the utility, point of supply is where you supply, and your equipment are here in this part. So, the transformer is not your property, but here in the HV connected one, transformer is your property and your responsibility also. If the transformer fails, you must repair it, you must replace it, but here if the transformer fails, utility will replace it or utility will repair it, because the point of supply is here, right, point of supply is here, but here the transformer protection everything you must look after when it is a HT connected scheme, HV. So, large maybe above 1 megawatt and above all are high voltage connected or the 33 kV voltage connected schemes, and the other systems are operating, auto reclosers and other distribution system components are in the system. So, that is why we call it an embedded generator. We have embedded the generator into the distribution network, right, into the distribution network. Then they talk about embedded generators with substantial captive local loads. So, there are, for example, some people have developed mini hydropower plants in tea estates, tea estate owners. So, their intention is use part of the output for their factories, tea factories, and maybe their bungalows and other things, and the balance they want to sell, right, balance they want to sell. So, that is why it has a substantial captive load. So, while it having a captive load, the balance they can sell, right. These generators will regularly operate in parallel with the CB network, but supply the power requirement of a localized industrial or other facility. The embedded generator and the load, when considered in together, may either be a net importer or net exporter of the electrical energy from CEB. Usually, there will be no special transmission or distribution lines built for the specific purpose of connecting the embedded generator. The connection will be through the point of supply from the CEB to the captive local load. That is, the owner has developed a power plant, maybe a solar plant, maybe a hydropower plant, right, and connected to his use, and if there is any excess, you sell it to the utility, right, just like some of the rooftop PV systems. You use your generation, excess you sell. If there is an excess, there may be sometimes no excess, right. If there will be import and export meters, whichever has done higher, you will have to pay. If you have imported net amount is more, you will have to pay. If the network has taken from you a net amount during the month, network will or utility will pay you. Then the embedded generators with minimal local load, then a separate agreement required to import energy, and so on. So, all these are described in this guide. Then the procedural issues I will not read, how to make an initial application, etc. So, all of them are described here, right. So, similarly, any utility in India also might have similar procedures laid out, how to proceed with the request. This letter of intent is a legal document. Once the letter of intent is issued to you, you can go to a bank and say, I have a LOI, I have a letter of intent from CEB for this power plant. Therefore, I want to negotiate a loan with you. So, when you have the letter of intent, you have a legal hold on the project, right? You have a legal hold on the project. In the reservation of the source, here is a typical single line diagram for the interconnection needs, right. So, various protection systems that are required, right, overcurrent, earth fault, neutral voltage detection, etc., right. Some of these things you might have studied under your protection studies. So, we can see that what we study in universities in separate modules are applied in the field in an integrated manner. You need protection knowledge, you need distribution knowledge, you need cable sizing knowledge, and you need knowledge on the cable generators, motors, and there are different modes of operation. So, we learn these things in different modules in the study program, but when we apply, we have to apply them in an integrated manner, combining all the knowledge. Here you can see there is a earthing transformer, right, earthing transformer, because there may be that voltage may be different from the low voltage, right. Here you can see a new situation, right. So, suppose your transformer is earth here. Now, here you can see in this transformer, I do not know whether in India the distribution transformers are delta star or not, right. In Sri Lanka, we have delta star, high volt 33 kV side is delta, low voltage side 400 volt side is star, and at the transformer neutral is solidly earth, right. That is the system they are operating for the protection systems, right. And then a new situation arises. Now, your generator is here and synchronized by this breaker, right, and the so the generator is connected, right. But if you earth the generator earth also, there are two earth systems, two earths in the low voltage system, and if you do that, what happens? There will be circulating currents, right, there will be circulating currents. To avoid that, what we do is we keep this, there is a contactor here, we keep it open. So, during normal operations, this is closed, this is open. So, neutral is not earth of the generator. Now, we would consider the situation this breaker trips, this circuit breaker here trips due to some reason in the network side. Now, our generator may be running with the loads available in the power plant, with the loads available in the power plant. If the suppose the water is very low, it had a very small load, small generation, it will balance the load requirements of your power plant and it can run. Now, you have a system here without an earth. Earlier you had the earthing point from the transformer. Now, since this breaker circuit breaker 2 is open, now the earthing is not available for the power plant side. Then it is like this. So, moment this breaker trips, this contactor will close, right, this contactor will close and make an earth for that system, right, make an earth for that system. So, I can read it here, generate a neutral earth contactor to be interlocked with other breakers to ensure safe earthing in all operating conditions. For clearance of faults inside the generator, obtain advice from the manufacturer, right. So, they have given this idea. So, this is to make sure that you have an earth, otherwise if you do not have earth system here, your circuit this earth leakage circuit breakers will not work, right, what you call the trip switches. So, earth leakage circuit breakers will not work unless you have a earthing point, then only the circuit can be completed and the ELCB can operate, right. So, if you do not do this, there is a safety issue, right, there is a safety issue. So, I am just typically showing you one point, you know, that all these are addressed in these guidelines, protection guidelines. That is why it is important to adhere to them, right. Then it talks about point of interconnection, and various other formalities, and the operational information to be provided, and so on. So, this is the procedural part of this guideline. The part 2 is the technical part, and then the metering equipment, who should bear the metering equipment, etc., all are described here, and there are classes, accuracy classes, because you can see now in a household meter, normally it is about class 2 meter, that is there could be about 2% error, right. But for bulk power like this, bulk power selling, you must go for at least class 0.5, right, but those meters are bit expensive, and the CTs and PTs should also have similar accuracy. Otherwise, your metering will be, you know, erroneous, means you will have a big loss on your part, or if on the other side the utility will lose. Therefore, big energy sales you should go for higher accurate energy meters like class 0.5 meters. Then the interconnection certificates. So, they will do a testing. Once you have completed the part, you have internally commissioned it, utility will come and do a fully testing whether you have done it as per this guideline. Can see testing and acceptance procedure. Once the testing has been successful, only you can grid connect and operate your power plant, right. Without this test certificate, you can't connect it to the grid. Then the testing procedure, they say, right, they will test various technical parameters, right, and then indicate if there are any discrepancies. Otherwise, they will issue a test certificate saying it complies with the requirements. Okay. So, other things are the various forms, etc., and then there is this part 2 of the guideline. This is the part 2 of the guideline. This is more technical. Protection and operation of grid interconnection, right, embedded generators, and the protection and operation of grid interconnection. This is the first part, it gives the entire thing, and we should look at the part 2. This is the part 2 that we are looking at, right. Studies and information to be exchanged, stability, fault level, protection, voltage level. For example, now you must know from the utility what is the fault level at your point of supply. It will depend upon the grid parameters, and then you must communicate that fault level to your equipment supplier, right, your equipment supplier who will be supplying various electrical components, panels, etc., and the synchronizing breakers, synchronizing panels, and the protection panels, all will be supplied by different agencies. But for them you must communicate what is the fault level at the power plant. Then they will design their system to, you know, withstand those fault currents. If the fault currents exceeds the design values, your panels will break down, right. They must, because you can see even if you look at a breaker, you will see it will be saying what is the short circuit current it can withstand, right. So, it should be compatible with the fault level at the network. So, the network operator will tell you what is the fault level at the network to be used in your designs, which you must communicate with your equipment or electrical equipment supplier. You can see fault level, general fault level information, fault level calculation, fault level reduction and mitigation, right. Because more embedded generators are connected to a location, as you increase the number of embedded generators, fault level goes up. So, that is one problem with the for the network operator. Now, suppose there is a hydropower rich area. So, one by one hydropower plants are coming and getting connected to the distribution network, right, and each time a generator is connected, fault level will go up a little. So, when you have too many, fault level will come to a level where the utility equipment have been designed. So, if you connect more generators, then the utility will have a problem, because their bus bars, their insulators, and they have been not been designed for such high fault currents. Therefore, on this ground also they might refuse to accommodate more embedded generators, because the network fault level is exceeded, right. That is also a concern for the utility. That is why they are very concerned, and they have put all these values here. Then the synchronization of the generators, right, general voltage fluctuation, synchronous generators, asynchronous generators, that is induction generators that we talked about, other types of generators, synchronizing check relay, and they will give the parameters for the synchronizing check relay, right. By the time you close the synchronous breaker, what is the maximum angle that you can have between the phases, R to R, Y to Y, what is the angle difference, how many degrees, 3 degrees, 6 degrees, they will say it should be specified to your manufacturer. So, the synchronizing check relay will then make sure by the time the breaker is closed, these are satisfied. What is the maximum difference between voltage magnitude by the time it is the breaker closes, and the speed etc. All these things are checked, right. Then the islanded operation, hazardous islanding, unearthed operation of the distribution system, low of fault levels, out of synchronization recloser, voltage levels, quality of supply. So, we do not have time to thoroughly study this, but I am just browsing through it, so that you get some idea, and then you can make sure that you get hold of the relevant grid code for you, and then accordingly design your systems. Remember, this is not only for mini hydro. Nowadays, we have a lot of solar projects coming up. For them also these apply when they come and connected to the distribution network. Some large solar projects are connected to the transmission voltages. So, this will not apply to them. Then they should look at the transmission grid code, transmission grid code. So, this is for the generators to be connected to distribution network. Again, you can see some good set of definitions. For young engineers, you must read all these definitions to be to remove any ambiguity in your knowledge. You can't have two meanings, right. They are, you must know exact meaning. Now, here you can see, for example, the utility may analyze the effect of implementing the additional generation on the stability of the utility system. Local stability will be studied when the additional embedded generator has a capacity greater than 5 megawatt, or makes a total generation capacity on a single distribution line greater than 5 megawatt. You can see. So, in the line that you intend to connect may have already a 2 megawatt generator connected by somebody else, and now you are proposing a 3 megawatt. Now, when your 3 megawatt one is proposed, the total is exceeding 5 megawatt now. So, therefore, the CEB will say we need to have a stability study. Stability study will check if this plant trips, suddenly, whether the system can remain in synchronous operation, whether there can be any problems for the network operation, right. So, they will do a simulation study and check. You can see it states sometimes it says this may be waived by the CEB for small embedded generators, typically less than 1 megawatt. Then they talk about fault level, right. The generating company shall provide information on the 3-phase symmetrical subtransial fault contribution to the point of supply, when the fault level information shown in annex 3 of the part 1 of the guide is provided to CEB. The cumulative effect of the embedded generator shall be assessed by the CEB. A study will be conducted when the cumulative fault level on distribution system reaches 90% of the rating of the associated distribution switch gear, right. That is, they will allow you to connect distributed generators until the fault level reaches 90% of the designed fault level of this utilities equipment, beyond which they will not allow. Then the protection requirement, voltage levels, interconnection voltage, etc. So, they talk about all these things, voltage flicker, voltage rise, studies on voltage flicker and voltage rise. I will not go into read all these things. Load flow studies, fault level calculation, make fault level, break fault level. So, all these things are discussed here. Then the voltage regulation, power factor requirement, earthing of electricity network and the embedded generator, right. Compatibility of network and generator earthing, generator parallel earthing, I will skip some of these things. Design of the earthing system, they have various requirements, synchronization of generators, voltage fluctuation, synchronous generators, asynchronous generators. Here synchronizing check relay, you can see the requirement for the synchronizing check relay, right. Typical relay settings will be plus or minus 20 degrees of phase angle. So, the by the time the breaker is closed, there should not be a difference of more than 20 degrees difference between the two phases, the phase angle, right. Maximum difference in the voltage of supply of 7% of the same nominal voltage, maximum shift frequency of 0.44%, a time delay typically of 0.5 to 2 seconds on the operation of the relay is commonly used to ensure the slip frequency is within limits. Hazardous islanding, right. The potential hazards presented by operating a generator in an islanded situation, unearthed operation of the distribution system, low fault levels, out of synchronization recloser, voltage levels, quality of supply, risk to maintenance personnel, right. Because they assume the generator has tripped, but now it is working stably with the part of the network, which is dangerous. So, they go and try to do maintenance and the system is still live. So, we must have adequate protection that such things are not possible. Frequency relay, local generator instability, islanding detection and protection. So, all the relay settings etc., they will tell here, level of HE point of connection plus or minus 10%. So, all are there. So, in your relay in the commissioning stage you must set all your relays to these values, right. Otherwise, when the plant is tested, they say your plant does not comply with the grid requirement. Over and under frequency. Here you can see the setting levels plus 4% minus 6%, that is 52 hertz and lower side 47%. So, you must set the frequency relays to trip at these levels, under frequency and over frequency trippings. So, you can't set it to something else, because then there will be nuisance trippings. there is no requirement for a time delay. The tripping time shall be less than 0.5 second. All of this are specified. Then the rate of change of frequency df by dt. You can see true rate of change of frequency operation is specified for some situations in section 8. Limits 2.5 hertz per second df by dt. This has been specified to ensure that there is minimum spurious trippings. Right? If the frequency is dropping more than 2.5 hertz per second, the plant should trip or should be shut down. Voltage vector shift, then settings, reverse VAS, intertripping, all of them are specified. So, you must adhere to the values given here. It may be different from utility to utility, right. So, you can't use one utility's embedded guidelines with the other utility in another area. Neutral voltage displacement protection. But as a hydropower engineer, you need not to be an expert on these things, right. So, you must know these things are there. So, you must ask your electrical engineer, right. He is a expert in the electrical field. So, go through this and make sure we adhere to this. So, he will go through these reports and then accordingly commission the plant. The hydropower engineer is not an expert on all the things, right. But you must show him that this is the grid code we have to stick to, and therefore comply with that. Here you can see different capacity generators require different levels of protection, right. So, different capacities will say, they will say if the capacity is large, increased amount of protection, right. Here you can see a maximum site installed capacity less than 5 megawatt, right, less than 5 megawatt, case 1, case 2, case 3, case 4, case 5, right. So, some are less than 5 megawatt, some are case 4 more than 5 megawatt, So, then what are the applicable protection level? Under and over voltage protection required for all cases. Here you can see all cases under and over voltage requirement, under and over frequency required for all cases. Vector shift protection required for case 1, 2, 3, right, not for these, maybe that is also for all cases. Here may be a mistake. Then the rate of change of frequency protection. So, only for some cases only, right, and NVD protection for some cases only, loss of phases for all cases. So, you can accordingly, now looking at your plant's capacity, you can see what are the schemes relevant to you, right, relevant to your plant. Then they further describe case 1, right, case 1. Protection required, design criteria, and then for the case 1, what is the single line diagram, what are the protections required, right. So, it is less than 5 megawatt capacity, and then case 2, right, all types of generators whether synchronous, induction, the installed generating capacity is less than 5 megawatt, but with a captive load, right. So, what are the protection requirement, what are the things that are not relevant for this scheme. Then the case 2 interconnection protection arrangement for less than 5 megawatt and with a captive load. Here you can see the captive load is here, right. There can be one generator or there can be several generators, that is why they have kept the provision as generator 2. all types except mains excited generators defined in cases 5. The installed generating capacity is more than 80% of the minimum captive load and capacity less than 5 megawatt. Then what are the protection required for that? And the design criteria. And then the typical protection arrangement for this case. Case 4, all types of generators. The installed generating capacity of the embedded generator site is greater than 5 megawatt. So, this is more than 5 megawatt capacity. Then the protection required. Design criteria, and this is the typical interconnection protection arrangement for a plant more than 5 megawatt in capacity. So, if you do not follow this and do it, what happens? By the testing and commissioning stage, utility will come and say you do not comply. Then you have to have additional cost to redo, correct it and redo it. Case 5, again same information, right, with the typical connection diagram. Then the surge protection they talk about. What are the surge protection you should provide? Location of the arresters, earthing, selection of the lightning arresters, service life, generator directly connected to low voltage overhead lines, that is for the small plants like rooftop solar which are connected to the low voltage. Then they talk about harmonics. What are the allowable harmonic distortion levels? Operational procedures and requirements, means of isolation, earthing facilities for maintenance, safety aspects. Okay. So, I just wanted to expose you to the requirements of planning the entire electrical system and also grid interconnection requirement, right, because we are connecting a generator to a healthy grid that is available. So, we should our generator should not pose any threats to the healthy operation of the existing distribution network, because the distribution network is connected to the public, factories as well as households and other utility, other users. So, their safety is a prime consideration of the utility, right. So, if our network, our system goes and disturb them, introduce more harmonics, right. So, that is a problem. So, that is why for example, rooftop solar, when they connect, they particularly check whether the total harmonic distortion should be less than 5%, because lot of switching are there. There's inverter, when the inverter switching are there, the sine wave is disturbed. Therefore, there will be more harmonics. Therefore, bad inverters will introduce higher levels of harmonics. That is why they are checking. Okay, there are other information available as annexes that we do not have to go through. So, with that we come to the end of our discussion on these electrical systems and their operations, right. And so, if there are any questions from online or physical participants, I would like to take. Otherwise, our entire discussion on our this hydropower implementation at this level from a hydropower engineer's point of view come to a conclusion, and we hope to have a tutorial maybe tomorrow to freshen up you with some more knowledge. If there are any questions I can take, otherwise we will conclude here.